My name is SeKang Kwon from Gyeonggi University. Gyeonggi University, Korea, and it is joint work with Dr. Dong-eun Ha and Professor Jong-san Kim. And I'm going to talk about simulation of general quantum measurement on a quantum computer. And basically, this we can only perform projective measurements on a quantum computer. So we asked, how do we more general measurement on a quantum computer? So the answer is today's talk. Here is outline. First, at preliminary section, we introduce notations and key ideas of the simulation protocol. And the next section, we introduce the simulation protocol. And then we show our implementation results. And we finish with summary and future works. As you know, positive operator value measure is a set of positive operators whose sum is equal to identity. And especially we call it projective measurement if the every measurement operator is a projector. And sometimes we represent the measurement operator in a cross operator form. And cross operator, which is satisfying this relation. This is a quantum measurement diagram, but in the previous talk, it is already explained, so I skip this. Here, I'm going to explain that every quantum measurement is simulated by sequential two-outcome measurements, and this diagram describes this. So let's see. At every node, we perform two outcome measurement. And at first, we measure E0 click or not. So if E0 clicks, then we finish this process, and else if E0 did not click, then we go ahead the next step and we measure the next two outcome measurement. So in this node, we measure E1 click or not, and by repeating this process, we can simulate the entire measurement and this. And here, I describe the measurement operator mathematically. Just that. In this slide, I put them together, but we have a problem. The problem is that we cannot guarantee that these operators have full rank. So we must resolve this issue. So in this slide, I explain how to resolve the issue. So let's assume that this matrix does not have full rank and have this form of spectral decomposition. In this case, this inverse matrix is defined on the support of itself. So that is, inverse matrix is defined like this by using spectral decomposition. And you must note that lambda I inverse is substituted by 0 if lambda I is equal to 1. So by using this definition, we can resolve the issue, and this description is valid. And to implement these measurement operators on a quantum computer, we need to modify, we need some modification at this measurement operator. E0 bar is same as this operator. We separate it into a pair of square root operators. Yes. Then, and repeating this kind of separation, finally we get this kind of form of measurement operators. A little complicated. And we will use this form in the protocol. Until now, I explained one of key ideas of the protocol, and here I explain the another one. So we are given measurement represented like this in a cross representation by Neymark theorem with ancilla system B with dimension n. There is known that there exists unitary operator acting on this space such that transform this state into this state, right hand side. So with this space, with this state, we measuring the system B with this projective measurement. We have probability distribution like this, and the right hand side is equal to same as the original probability distribution performed by this measurement. So we have same probability distribution, and also the post-measurement states are same each other. So we can simulate the measurement by projective measurement yes. So in this section, I introduced the simulating protocol. In the previous slide, we have seen that there is a unitary operator transforming size 0 into psi f. So what we have to do is to calculate this unitary operator. But to implement this unitary operator, we have to decompose it into basic quantum operations. I mean, single qubit operations and C-naughts. So our protocol is all about this decomposition. That's all. First, we deal with two outcome measurement. So here we are given two outcome measurement in a cross representation. First, we do singular value decomposition of measurement operators like this. Here, V1, U, and V2 are unitaries, and D1 and D2 are diagonal matrices. Step 2, we decompose the above unitaries into two-level unitaries. I mean, these two-level unitaries is two-level unitaries means that it acts on only two-dimensional subspaces, and for each unitary, we need at most this quantity of two-level unitaries to decompose. And again, we decompose those two-level unitaries into single qubit operations and C-naughts. And final, we make a quantum circuit and run. So based on the protocol, we can compose quantum circuit. The two-outcome measurement is given in a cross representation, and psi 0 is the state to be measured, and M0 and M1 have spectral, SVD. Using these facts, we compose quantum circuit like this. This is my drawing. Sorry about that. I drew a zigzag line. I drew a zigzag line here because I want to represent that system A is an arbitrary qubit system, and system B is in a qubit system. So I drew a zigzag line here, and this theta gate is rotation y gate, and rotation y of 2 theta I is little different to our convention. And this controlled gate means that controlled rotation y gate of theta I, and it is activated when the control state is in I state. So system A is a QD system, so we have D kind of controlled gate like this. Yes, so let's move on to the N-outcome measurement protocol. Here we are given N-outcome measurement in a cross representation. So step step one is measurement operator decomposition. At first, step one dash one, we do single value decomposition of M0 like this, and spectral decomposition of E0 bar like this. And after that, we do singular value decomposition of M1 tilde, defined like this. And from M1 tilde, we can get decomposition of M1, the original measurement operator, like this. And repeating this process at final, we can get this kind of measurement operator decomposition. As this complexity it came from the complexity of measurement operators you have seen in the previous slide. And step 2, 3, 4 is the same as the two outcome measurement. So let's make a quantum circuit. We have this measurement operator decomposition, and quantum circuit is here. In the previous slide, we have seen that this quantum circuit, this works as a module of the larger quantum circuit. So each module performs two outcome measurement like that. So we need n-1 circuit modules like this. Here we show our implementation results on I-band quantum and on I-band quantum and ion Q machines. First, example 1. This is three outcome single qubit measurement. The prepared state is 0, and measurement operator are like this, where psi I is defined like this. This is measurement operator decomposition, and this is circuit diagram on cascade. So first implementation result is on a air simulator. There is no noise, ideal situation. So in this case, it fits well with our probability calculation. And next, this is real quantum machine, IBM pulse. There is some noises, and the red box histogram, this should have been 0, but because of noise, they are also detected. But the shape of the distribution is similar to each other. Scale is different anyway. And this is ion Q harmony result. there is also some noises. So, and this stage should not been detected, but because of noise, they have been detected. In this case, we have similar shape with the ideal one. Okay, so in the example 2, in this example, we implement 3-outcome single Q-treat measurement. So in this case, prepared state is 0 state in C3, and measurement operators are like this, similar to the previous example. And we added this term in M0. So this is measurement operator decomposition. This is circuit diagram. But the quantum computers are based on the qubit systems, so we have to embed to qubit systems. So this is embedding process, but very trivial process. So these are our implementation results. First, this is noiseless simulator. This also fits well. And this is results on IBM Nairobi, but there is so many noise, so we cannot get meaningful data from this. IonQ harmony is like a uniform distribution, so there is no meaningful data too. So let's look at the compiled circuit. But compiled circuit is very large, so I take the screenshot of a part of it. In the IBM Nairobi, there is so many swap gates and CNOTs. So in the compiled circuit, there is 387 CNOTs total, and in the IonQ harmony, there is also many CNOT gates and multi-qubit CNOT gates like this. This is IBM spec of IBM Nairobi. The CNOT, the median of CNOT error is about 1%. So we can estimate the gate fidelity about 99%. So simple calculation, we can get these results, and this means that we can get 2% of accuracy. So this is the reason for our bad result. So we summarize our talk. First, I introduced our measurement simulation protocol and showed implementation results on IBM Quantum and IonQ. And as a future works, we need to analyze complexity. But it's just simple calculation, I think. And to improve circuit depth is also interesting stuff. And to seek another protocols is also interesting, I think. So that's all of my talk. Thank you.
Questions, comments?
Put into play how your approach is different from the ones used in the paper that you cited.
The different thing is we implemented on Q-tree system. The paper is only implemented in a single qubit system. So that's the difference.
Any other question? Okay. So if not, let's thank the speaker again.